Hello, this is the Mathematic Fanatic, and you are watching Cool Sum of the Fibonacci Sequence's Big Brother. So a little introduction. This is a follow-up to my last video where I showed the following sum. The sum from k equals 0 to infinity of f of k plus 1 all over 2 to the k, which equals 4, where f of n is the Fibonacci sequence defined by f of 0 equals 0, f of 1 equals 1, and f of n equals f of n minus 1 plus f of n minus 2 for all n greater than or equal to 2. If you haven't seen it, I recommend watching it, but you should still be fine since it will be going over some of the same concepts. After posting that video, I found a Michael Penn video on the same sum with a minor difference. I linked his video in the description of the last video. Today I will be doing a very similar sum with the sum of the Tribonacci sequence, which is defined by t of 0 equals 0, t of 1 equals 1, t of 2 equals 1, and t of n equals t of n minus 1 plus t of n minus 2 plus t of n minus 3 for all n greater than or equal to 3. The sum will be the sum from k equals 0 to infinity of t of k plus 2 all over 2 to the k. So that means the difference is, instead of a k plus 1 in the function, you have a k plus 2, and instead of the function being the Fibonacci sequence, it's the Tribonacci sequence, which, as we defined earlier, is this. So, the sum of the Tribonacci numbers. Well, last time I showed you guys the sum of the Fibonacci numbers, the first n of them. So firstly, we want to prove by induction that the sum from k equals 0 to n of t of k equals 1/2 times t of n plus 2 plus t of n all minus 1. For these base cases, we will show that it's true for n equals 0, n equals 1, and n equals 2. For n equals 0, we just get t of k at 0, so t of 0, which equals 0. So, and we know that because 1 plus 0 minus 1, the 1's cancel out, it becomes 0, so that's true. But we know that the second Tribonacci number, indexing at 0, is 1, and the 0th is 0. So we get what we wanted to show. For n equals 1, we get t of 0 plus t of 1 equals 0 plus 1, which equals 1, which is the same as 2 plus 1 minus 1 all over 2, which is exactly what we wanted because t of 3 equals 2 and t of 1 equals 1. And I forgot a parentheses there, but it shouldn't matter. For n equals 2, we get t of 0 plus t of 1 plus t of 2, which equals 0 plus 1 plus 1, which equals 2, which equals 4 plus 1 minus 1 all over 2, which is exactly what we're looking for because the fourth Tribonacci number indexing at 0 is 4, and the second Tribonacci number indexing at 0 is 1. Now assume that is true for n equals m. We want to show that it is true for n equals m plus 1 in the following way. We have the sum from k equals 0 to k equals m plus 1 of t of k, which equals t of m plus 1 plus the sum from k equals 0 to k equals m of t of k. That's because I just pulled out the last term, which then, because we have the inductive hypothesis, we assumed that it is true for n equals m, we can substitute that in, which gives us t of m plus 1 plus 1/2 t of m plus 2 plus t of m minus 1. The t of m plus 1 can be separated into 2 halves times t of m plus 1. So then you can keep one of them out and plug the other one in. You end up getting 1/2 times t of m plus 1 plus 1/2 all times t of m plus 2 plus t of m plus 1 plus t of m minus 1, which the t of m plus 2 plus t of m plus 1 plus t of m just sums up to t of m plus 3 based on the rules of the Tribonacci sequence. So therefore we get the sum we are looking for. So two ways of finding the sum. Michael Penn finds the value to the sum in my last video by using generating functions, which I will take inspiration from for this video. The sum we are trying to find today is the sum from k equals 0 to infinity of t of k plus 2 over 2 to the k. Since in the last video we used a probability model, we will do that again, but I will use that as the second solution this time instead of the first. So for generating functions, a generating function is a power series that uses a dummy variable to make an easier solution to a specific problem by turning it into a general form. The power series we will use to find the generating function is the following. the sum from k equals 0 to infinity of t of k times x to the k, which equals x plus x squared plus the sum from k equals 3 to infinity of t of k times x to the k. And that's because I just took out the first, second, and 0th terms. The 0th term just goes to 0. The first term is 1 times x, and the second term is 1 times x squared. So that's where I got those from. Since we know that the sum of t of k can be expanded into t of k minus 1 plus t of k minus 2 plus t of k minus 3, we can actually do that right now, which can be simplified to x plus x squared plus x cubed all times the sum right here. And that's because we're actually indexing from 0 to infinity on this sum, whereas we're indexing from 3 to infinity on these sums. We can then combine the term with the t of k in it, which would give us this following sum, which gives us x plus x squared plus x cubed all times the sum from k equals 0 to infinity of t of k plus 1 plus t of k plus t of k minus 1 plus t of k plus 1, all times x to the k. So that just ends up giving us x plus x squared plus x cubed all times this sum, and that's because we just combined the t of k plus 1s. However, since t of negative 1 is not defined, we can consider it to be 0. So we actually get this. This is what we had before up here, and then this is what we're actually finding. And that's because we have x plus 1. Where did that come from? Well, if we were to change this t of k minus 1 into t of k, we would kind of have to do that by re-indexing, right? So this part would be the sum from k equals negative 1 to infinity. But we know that t of k equals negative 1 is 0. That would mean we would actually need to add 1 to the exponent of x to the k, because we're adding 1 to the k in all terms. So that's where we get this x from, because it's x plus 1 times x cubed. Then we can put the terms with t of k on the other side, like we did before, and we are left with 1 minus 2x cubed minus x to the 4th, all times the sum we originally set as the generating function, equals x plus x squared plus 2x cubed, all times the same sum, but with a plus 1 in the t term instead, which we can finally convert to this, which I actually just realized I wrote the exact same sum next to each other, but we can convert this to this. Since t of 0 equals 0, we can pull this over to the other side, which gives us 1 minus 2x squared minus 2x cubed minus x to the 4th, all times our generating function equals x plus x squared, which we can then divide this part out from both sides to end up giving us our generating function equals x plus x squared all over 1 minus 2x squared minus 2x cubed minus x to the 4th. However, that's not in its simplest form, because we know that the numerator has a factor of x and x plus 1. So that means we can check to see if x or x plus 1 divides out from this side. And x does not, because the 1 term. But the x plus 1, it does actually divide out, which gives us our new generating function, x over 1 minus x squared minus x cubed. And that's our total generating function. And finally, since we're looking for the sum from k equals 0 to infinity of t of k plus 2 times x to the k, rather than t of k times x to the k, we can increment k in the following way. Finally, we can make the lower bound 0 again by plugging in the values of negative 2 and negative 1, which negative 2 gives us 0, and negative 1 gives us x. So that gives us x plus x squared all times the sum from k equals 0 to infinity of t of k plus 2 times x to the k, which equals what our original generating function is, because this is the same. And plugging in x equals 1/2, we get the following. I just subtracted x and divided by x squared already, so that gives us this, which gives us, this is the x squared term that I divided out, this is the generating function, and this is the x that I subtracted, which as you can tell, goes to 2 over this big thing, all minus 2, which is 2 over 1/8, because this all simplifies to 1/8, which gives us 16 minus 2, which gives us 14. So that's our solution, 14. Now let's use a probability model. So in my last video, I used the probability model of the sample space defined by flipping a fair coin until you receive heads twice in a row. This time the probability model will be a fair coin until you receive heads 3 times in a row, and then stopping. I will prove that this sample space has the Tribonacci numbers as its number combinations, per number of coin flips n. Let a function f of n be the number of possible sequence combinations of coin flips of length n. Then we know for our sample space, f of 0 equals f of 1 equals f of 2 equals 0, because we always keep flipping until 3 heads in a row. So there's never a stopping point at 0, 1, or 2 heads, or coin flips in general. For f of 3, we get only HHH, so we know f of 3 equals 1. For f of 4, we either flip tails once, then get 3 heads in a row, or we keep going because we don't get heads, or we stop at 3 flips because we get 3 heads in a row right away. So f of 4 equals 1. We could also break f of n into 4 different functions: f sub tt of n, f sub ht of n, f sub th of n, and f sub hh of n, such that f of n equals the sum of those 4 parts, where f sub tt, f sub ht, f sub th, and f sub hh are the number of combinations of length n that start with tt, ht, th, and hh respectively. Then for f sub tt of n, we know that for a sequence to start with tt, the sequence that follows the first flip clearly starts with either tt or th, because otherwise the next starting flip would not be a t. So we get the following: f sub tt of n equals f sub tt of n minus 1 plus f sub th of n minus 1. The same goes for f sub th and f sub ht with the respective changes. However, for f sub hh, we do not get that, because the sequence of length n that starts with hh is followed by a sequence of length n minus 1 that starts with hh. Then we should be done at n equals 3 with hhh. Therefore, we know that f sub hh of n equals just f sub ht of n minus 1, because we can't actually get heads 3 times in a row without stopping. So now we can assume that f of n equals t of n minus 2, for lowercase n equals capital N minus 2, capital N minus 1, and capital N, because we found that the base cases work earlier. Then prove that f of n plus 1 equals t of n minus 1. We do the following: f of n plus 1 equals the sum of all the partial functions, which can then be broken down further using their definitions of the partial functions to get 2 times each of the partial functions, except for f sub hh, which we only get 1 of the previous. So we go from 1 of each for n plus 1 to 2 of the first 3 for n plus 1 of the last one for n. So that gives us 2 times f of n minus f sub hh of n, because we can only use the definitions of those functions. We can follow it up by 2 of f of n minus f sub hh of n equals f of n plus f of n minus 1 plus f sub tt of n minus 1 plus f sub ht of n minus 1 plus f sub th of n minus 1 minus f sub ht of n minus 1. And that's because we're using this right focused at n, so these would be n minus 1 each. And instead of combining these into this, for n minus 1, I ended up keeping one of the n minus 1s, and then I ended up keeping the other 3 that we had rather than subtracting the one that we don't have. So that ends up canceling out the f sub ht's, right? Which gives us f of n plus f of n minus 1, which the f sub tt and the f sub th can each be broken down into their respective parts here, which just equals f of n minus 2. So we get f of n plus f of n minus 1 plus f of n minus 2, which finally we can do the finale of induction, which is f of n plus 1 equals f of n plus f of n minus 1 plus f of n minus 2, which we assumed it was true for capital N minus 2, capital N minus 1, and capital N. So we get t of n minus 2 plus t of n minus 3 plus t of n minus 4, which by the definition of the Tribonacci sequence equals t of n minus 1. The sum we want this way. Well, we know that from the calculation that the number of combinations of coin flips of length n is the same as the n minus 2th Tribonacci number. And we know that a sequence of fair coin flips of length n has a probability of 1 over 2 to the n of occurring. So we get the sum of the sample space from k equals 3 to infinity of t of k minus 2 all over 2 to the k, which equals 1 because it's a sample space, which gives us the following equals this based on changing the bounds of the summation from 3 to negative 1 to get a t of k plus 2 in the numerator, which then we can end up getting rid of the term for k minus 1 and adding it separately, which is what we get here, and then multiplying by 1 over 2 to the 4th, which is 1/16. So this is what we got here, which that still equals 1 because that's still the sample space. Finally, we can subtract 1/8 from both sides and multiply the whole thing by 16 to get the sum we are looking for, which gives us 16 times 1 minus 1/8, which equals 16 times 7/8, which equals 14. That is our sum. So in conclusion, we got another interesting value. And since we made a generating function for the value, we can actually do so many more different kinds of sums involving the Tribonacci numbers, way beyond our wanted sum. That being said, the reason I did not show the method of using the exact non-iterative value of t of n was because it is honestly way too long and wouldn't really make a lot of sense to me or you, so it wouldn't make good content. I hope this, however, did give you the content that you could enjoy. Thank you.